at a general strategy for approaching these word problems. Now, usually in math, these problems are difficult for people. Generally, people can do math if they see an equation or if they see a problem written out with numbers. But to move from words to numbers has been difficult for people, not only in math, but in all of the sciences, in chemistry and physics as well. And there's a knack for doing this, a way of looking at things that all of us who do these kinds of problems have found useful. I know that I had to develop this skill when I was learning math and doing physics, chemistry, and other sciences. Let's look now at that specific strategy. The first thing you need to do is collect information. Look at the problem carefully, and as you read it, try to understand what the problem is getting at, and try to get a picture in your head of what's going on. Try to visualize the procedures, the things they're asking for, the quantities. If it's cows and chickens, think of a barnyard with cows and chickens running around. If it's two cars coming together, close your eyes and try to see those cars coming together, or try to go from the printed word to some sort of a situation that you might have a feeling for that you can hold in your head, and that'll prove very useful to you. The next thing you should do is write out your analysis, just a few words about the steps you may use to actually get a numerical result for your problem. Then once you've written out that analysis, be it an equation or a description, then actually do the math, solve the problem, and finally check your answer. We're going to look at each of these steps very carefully and specifically, and then we'll apply them to do some problems. So here are the steps for doing the problems. The first thing you need to do is collect information. Read the problem very carefully. See what it is they're telling you, what kind of information you're given, and as they show you the information, ask, is there anything that's left out that you might need to fill in yourself? For example, they might not tell you there are 60 minutes in an hour or 60 seconds in a minute. That's considered to be general knowledge that you fill in yourself. The context of the problem will suggest these things. Read the problem carefully. Then collect the information. Write down very specifically in whatever kind of shorthand notation is best for you the information that's given. What are they telling you in the problem? And then what's asked for? What information is requested that you reach at the end of when you've done the problem? Then try to visualize, as I've said, what's going on in the problem. If possible, make some kind of a sketch and then label the sketch. So for example, this blue area might be a swimming pool, and the green area around it, some sort of border, for example, flagstone or something like that around the pool. So that helps you to visualize what the pool is, then label the sketch with the information that's given in the word problem. So for example, here I could put in that the pool is 14 feet across and 40 feet long with a 6-foot border around it. Looking at this will help me to understand what kind of math I must do and what sort of analysis I need to arrive at to be able to get to equations that I can then solve. We need to perform an analysis, and that is writing down any formulas or math principles that you can think of that may apply to what you're dealing with. For example, if your problem involves distance speed and time, you should know, or you will be given, that the distance you go is equal to the speed you go times how long you travel at that speed. So if it's that kind of a problem, write down that formula. There will be cues in the problem itself, in the written text, about what may apply to this. If you see the word the sum, you somehow know you have to deal with addition. If you see the word difference, you know that you somehow have to deal with subtraction. So this will help you in the analysis. Then it's also helpful, particularly when you're getting started, to write out a sequence of the kind of things that you need to do to ultimately arrive at a solution to the problem. So here are the steps. First of all, we go to the solution. To solve this, we have some kind of a formula that you may have written, and you substitute numbers for the problem into your formula. Then you evaluate what you get, the formula with the numbers in them, to get some answer. It's a numerical answer. And if you're dealing in units, not just pure numbers, you need to include those units. The units could be things like dollars, if you're dealing with a money problem, or miles, or degrees, or the number of cans, or the number of cases. The problem will usually specify something specific, and your answer needs to reflect whatever that specific solution requires. If you're asked how many people there are in a group, your answer should say something like 42 people in this group, so that your answer reflects what the problem has asked for as well as the number. Generally, your math teachers not only look to see if you've done the math correctly to get the correct number, but they also expect you to have a complete answer when you're finished with the problem. Finally, you should look at some way to check your answer to make sure that what you've got is reasonable. So, for example, if you are dealing with a problem that will give you a distance between here and Nogales, and you get 80,000 miles, you may wonder about the correctness of your answer. If you're asked something about a temperature and you get 300 degrees and the temperature is in your room, that's, water would boil. And so that would be an inappropriate answer. So always check to see if your answer is reasonable. You can also do this if you have started with an equation and got an answer. Put your result back for the unknown of the equation and see if your equation is still an equation. When you take your answer and put it back in the variables, the equation should balance on both sides. So reasonableness is an important criteria. You can also use units to check your equation. If you carry units through all of your calculation, units add, divide, multiply, etc., like algebraic quantities. And so if your units come out correctly at the end, then you know that, or at least expect that, your answer is also correct. Well, so much for all of the general information. Let's look now at actually applying these techniques to solving some problems. Here's one, and this is a pure number problem, just telling you in words the relationship between numbers. And it's 100% pure information because there's no one's names in it. There's no more information than you need to know. 4 more than 7 times a number is 18. Find the number. Let's mine this for information. First of all, what are we told? We're pure information. 4 more than 7 times a number is 18. And what are we asked for? We're asked to find the number. Let's see how we would do it. First, we would write down the information we're given. We say that there is an unknown number and related information 4, 7, 18. So here's the question. What is that unknown number? Let's try to visualize it. So it's 4 plus 7 times a number, which means there are 7 of them, and that plus 7 times whatever the number is must be equal to 18. Now, let's analyze this. First of all, we have n, an unknown. Then we're going to write an equation from the given facts and solve it for n. So let's look at the solution. Here's the equation, and let me say 4 plus 7 times a number is equal to 18. Then what we're going to do is use our methodology for solving equations by doing the same thing to each side of that equation and thinking of the equal sign as the pivot point. And our final strategy is to do what we need to do to both sides of the equation equivalently to get n by itself. So the first thing we need to do here is get rid of the 4 that's on the left of the equation. If I do that, I subtract 4 from both sides of the equation, and plus 4 minus 4 is 0. So on the left I can write 7n. Then if I've done it to the left, I need to do it to the right. 18 minus 4 is 14. So I'm left with another equation, 7n equals 14, but I want 1n, not 7 of them. So I need to divide both sides by a 7, and if I do that, 7n divided by 7 is n, 14 divided by 7 is 2. Now, I can check this. Remember, if I have 4 plus 7n equals 18, one of the ways we can check is by taking our answer and putting that back into the equation and seeing if what follows from it is still an equation. So 4 plus 7 times 2 equals 18. 4 plus 14 equals 18. Add those two, 18 equals 18. So we see we have a pretty good idea that our answer is correct at this point. Let's look at another problem which may actually refer to you a little bit. Rebecca, a conscientious Math 86 student, studies 3 hours each day, 6 days a week. If there are no holidays or vacation days, how much study time does she put in during a normal 16-week semester? Let's look at what's given and asked for. We're given she studies 3 hours a day, 6 days a week, and we want to know how much study time she puts in during a 16-week semester. Let's condense that information, and we're given she studies 3 hours a day, 6 days a week, 16 weeks a semester. And we have to answer the question, how many hours does she study each semester? Now at this point you should try to visualize what's going on and if possible make a diagram. Now it's easy to look at the diagrams I've made with the computer in PowerPoint, but let's take a look now at how you might make a diagram with a pencil and paper. So here you are doing your homework, and you think about the fact that Rebecca studies 6 days a week, and so let's suppose that we make a diagram here, and this is the semester going down this way, and we know that there are 16 weeks in the semester. So this is week 1, 2, 3, 4, and so on down. Then we know that she studies 6 days a week. So we can say, all right, 1 day, 2 days, 3, 4, 1, 2, 3, 4, 5, and 6. And she studies each day 3 hours, 3, 3, 3, 3, 3, 3. And there's 1, 2, 3, 16 weeks in the semester. So you see, I've made a very crude diagram, but it helps me to see what's going on, so that each week she studies 3 hours for 6 days, That looks like a multiplication to me. And then if I multiply that down by 16 weeks, I see I have a pretty good idea already of how to solve the problem just looking at the diagram that I did. Let's continue the analysis. So we see from the diagram that we need to multiply the number of hours per day times the number of days per week to get the number of hours per week. Then we need to multiply by the number of weeks in a semester to get the number of hours per semester. Let's solve it. So we have 3 hours per day times 6 days per week times 16 weeks per semester. If we do the math, 3 times 6 is 18, so we study 18 hours a week. Then we multiply that by 16 to get the number of hours per semester. And you see that our answer is labeled 288 hours per semester. Let's look at another one. The Pima College Bookstore buys textbooks by the carton, each of which holds 24 books. If 2,350 books are needed, how many cartons must be ordered? Now, let's read this and try to extract the information from it. So we have 24 books per carton, and we know that we need 2,350 books, and we're asked how many cartons. We need to summarize this information. We're given that number of books. We have 24 books per carton, and we're asked how many cartons. Let's analyze this then. We need to divide the total number of books needed by the number of books in each carton, and that will give us the number of cartons. Here is the solution. We divide 2,350 books by 24 books per carton. When we do the division, we see, first of all, we have exactly the number of books that fit into 98 cartons. And so we say that our solution is there are 98 cartons needed. Let's look at one that's slightly more complicated and interesting. A plumber charges $44 just to make a house call, and then $20 an hour for the time he or she spends on the job. If he bills Jane $224, how long did he work? Okay, let's go information mining. What are we given? We're given that the house call is $44 no matter what, $20 an hour, and the bill is $224, and what we want to know is how long did he work? So let's look at the summary of information. We're charged $44, $20 an hour. The total is $224, and we want to know the number of hours worked. So let's look at the analysis. What do we want to do? Then the total bill is going to be the house call charge of $44 plus the number of hours that the plumber has worked, which is what we need to know, times the charge per hour. So we need to write this out as an equation and then solve that for the hours. So let's translate this into an equation in the solution. So the total charge is $44 plus n hours times 20. Let's make that into an equation. So 224 is equal to 44 plus 20n, and we need to solve that for n, the number of hours the plumber has worked. We'll use our scale idea to solve the equation, and remember the idea is to isolate n to get that by itself to get the number of hours. So the first thing I need to do to get n by itself is remove the 44 from the right-hand side of the equation, so I subtract 44 from both sides. When I do this, it gives me 180 is equal to 20n. If I have 20 n's, I need to get what 1 n is, so I divide both sides of this by 20, and I find that n is equal to 9. So the complete answer is the plumber works 9 hours. A reasonable amount of time for a plumber to work on a big job. If I got the plumber works 30,000 hours, I might start to wonder about my solution. So also, if I wanted to check, I could go back and plug 9 into the equation where we have total charge and see, in fact, if that comes out to $224. Let's look at another problem. A concert hall has 7 sections, each of which has 23 rows with 14 seats in each row. If the theater sells out for a particular performance, how many people attended? If the average ticket sold for $20, how much money was collected at the box office? Reading this carefully, let's look for what we're given and what we're asked. So we're given that there are 7 sections, 23 rows, 14 seats in each row. And we're given that the theater sells out. We're asked how many people attended. Then we're given another piece of information that the average ticket is $20, and we're asked for how much was collected. Let's try to summarize this. So we're given 7 sections, 23 rows, 14 seats. And we're given that the average ticket cost $20. There are 2 questions asked. How many people in a full house? And how much money was collected by the full house? Our analysis is we need to multiply the number of sections by rows in each section, the number of seats per row to get the total number of seats, and we could try to visualize this as an array. We have 23 rows by 14 seats in a row, and your diagram can be a crude pencil thing. As long as you can clearly see the information in it, it doesn't have to look anywhere this nice, although of course with a computer it's very, very easy and nice to make beautiful diagrams. We have 7 sections. There are the sections. Let's work on the solution. We have 7 sections times 23 rows per section times 14 seats per row. So when we do the math, we see that we have 2,254 seats in the hall. Then we need to find out if the seats sold for an average cost per ticket, we need to multiply that cost by the number of seats. So we have 2,256 seats times $20 per seat. We do the multiplication and we find out on that particular night the theater grossed $45,120. Let's look at another question or problem that is more or less like that, perhaps a tiny bit more complicated. A movie theater charges $8 for adults and $4 for children. How much does it cost a party made up of 6 adults and 10 children to attend? Looking at it carefully, we're trying to find the information we're given and what we're asked. We're given $8 for adults, $4 for children, and we're asked how much does it cost if 6 adults and 10 children go to the movies. Let's summarize the information. We have $8 per adult for 6 adults and $4 per child for 10 children. And the question is, what's the cost for everyone? Let's analyze this. We need to multiply the $8 for the 6 adults and the $4 for the 10 children. Then we need to add them together to get the total cost. Let's solve the problem. We have 6 adults times $8 per adult, plus the 10 children at $4 per child. So we multiply 6 times 8 and get 48. 10 times 4 is 40. then we need to add the two together, so our night out at the movies cost us $88. Wow. Another problem. Barbara earns $8 an hour for the first 40 hours she works during a week, and $12 an hour for every hour after that. How much does she earn if she works 50 hours in 1 week? This problem requires quite a bit of consideration and analysis. Let's look at what we're given and what we're asked for. We're given that she gets $8 an hour for the first 40 hours and then overtime for every hour after that. And we'd like to know how much she earns if she works 50 hours in 1 week. Summarizing that information, we get $8 an hour for 40 hours, $12 an hour after or above 40 hours, and we know that her total time worked from the problem is 50 hours. How much has she earned? Here's the analysis. We first subtract the 40 hours from the total to get the number of hours she worked at $12, and then add the product of 8 times 40 to the 12 times whatever is left, which is 10, to get the total dollars she earned. Let's do it. So it's 50 hours minus 40 to get her overtime hours. Then we get the 8 times 40, which she would get at her normal salary. Then how much she worked overtime, $12 an hour times the 10 hours. Then we would add those together to get $440 per hour. And so Barbara during the week would earn $440.